Hello, everyone, and welcome to our presentation. My name is Daniel, and today we'll be discussing GNSS non-line of sight prediction and the opportunity to use neural city maps to improve our ability to navigate with environmental features in this urban setting. GNSS receivers in an urban environment have to deal with complicated disruptions to the GNSS line of sight signals coming from tall skyscrapers or lower buildings. These blocked or non-line of sight signals can disrupt the user's ability to efficiently localize themselves in the city. However, their understanding about which signals are line of sight and non-line of sight can change depending on if we use a more detailed understanding of the city, such as a better building model, and if we choose to include other objects, such as vegetation, temporary structures such as tents, and even bridges. Now, the key operation underlying our ability to understand and use the complex environmental and urban features in the city is non-line of sight prediction. So mathematically, this says that if I give you a user position and a line of sight ray to the satellite, I need to be able to predict whether the city would obstruct this line of sight ray. And this key operation of non-line of sight prediction permeates many modern urban navigation approaches. For example, we might consider the process of forecasting to determine which parts of the cities have better GNSS availability or better GNSS localization accuracy. In situ, we might also use it to mitigate the effects of these non-line of sight or block signals, or even use this as a feature in techniques such as shadow matching. So if we are able to improve non-line of sight prediction in urban environments, we have the opportunity to improve a large suite of approaches to urban navigation. Now, to improve non-line of sight prediction, we might look at the map. As motivated in the introduction, our current understanding of the environment is based off of our ability to encode the detail in our map representation. Current maps tend to use mesh-based or set-based approaches, and these approaches are particularly efficient if our understanding of the geometry is not very detailed. In that case, we can efficiently encode the understanding of the geometry and use it in real time. But as we approach scenarios where we have a more detailed understanding of the geometry, these map representations tend to suffer. Moreover, it tends to take a long time to generate these map representations, sometimes taking even decades. So if we want to encode a map representation that also includes objects such as trees, those temporary structures, and even bridges, we might want to consider the opportunity for generating and using maps that better match the user environment. And in this gap comes the opportunity of a neural city map. These two videos are completely generated from a neural network. On the left, we see the RGB color images, and on the right, we see the rendered image. What we can see is that the neural network not only understands the visual characteristics of the environment, but it also understands the geometric representation of the environment shown in the depth rendering. And this geometric understanding of the environment is what motivates us to propose neural city maps for non-line of sight prediction in urban environments. We would like to note that we also have, our co-authors have a related topic also in the ION GNSS Plus conference, where they discuss how to build up this neural city map from multiple regional neural networks and how that compares to the visual landmarks that we might see between the neural network generations and real in situ cameras. So we encourage you to look at that. But returning to this presentation, we really want to focus on how we can use these neural city maps for GNSS non-line of sight prediction. So moving into the outline, we'll be going over the methods and into the results. And specifically in the methods section, we'll be discussing why as a community, we should care about neural city representations and how we specifically use them for GNSS non-line of sight prediction. You might care about a neural city representation, as discussed in the introduction, if we really care about those details that impact our ability to predict non-line of sight. So a neural city map is able to encode this detail in a continuum, meaning that we're able to account for overhangs and other objects in the scene without having to interpolate between vertices or having to encode many, many vertices. It is also environment agnostic, meaning that the neural network doesn't particularly care if the objects in the scene are tall skyscrapers or hundreds of trees. The overall architecture, the way to generate the neural city map, and the way to use it remains the same. We also care that we can quickly and readily generate these neural city maps, even from few camera images. And what's more is that we can get these images from an aerial view, such as from a drone, but then query the neural representation at ground level, such as for an autonomous car or a pedestrian. And lastly, it is a compact representation, meaning that as we add more and more images, the overall memory footprint of the neural representation stays constant. However, there are some challenges that we need to be aware of. This neural city representation that we will be discussing is primarily from computer graphics, and the focus was on computer vision. However, this work, the main contribution that we're doing is bringing this into the GNSS community, meaning that we have to be aware of how this visual representation is different from the GNSS representation. We also have to be aware of artifacts from the neural city map that will impact our GNSS non-line of sight predictions. Specifically, we get unobservability haze in areas where we did not have observability in the training set. In those regions, the neural network tends to produce this haze, or floaters, as the computer graphics community calls it, which is a more translucent sense because the neural network does not know what to produce in those areas. With this in mind, the underlying neural object is this neural radiance field. Specifically, this neural radiance field is a fully connected neural network, which acts as a field, similarly to a magnetic field. So in a magnetic field, you need to be able to give me any XYZ point, and I have to be able to give you the strength of the magnetic field at that point. However, in this case, we have a radiance field, meaning that we care about the blockage density and the RGB value. That's going to allow us to reconstruct what we can visually see. And this is all encoded in a neural representation. We encourage you to refer to Gao et al. From University of Waterloo that provides a more comprehensive review of over 150 preprints on NeRFs just in the recent last 3 years. However, in this presentation, because we're specifically focused on the GNSS context, we're going to be focused on what matters for that scenario. We need the full neural radiance field during training because we will be building up our understanding of the geometry from camera images. Though at runtime, when we're doing GNSS non-line of sight prediction, we really care about this geometry network, which is the first half of the neural radiance field. Specifically, we can query any XYZ point, and it will tell us the predicted blockage density. Now, what does this mean for a map representation? Well, if we return to our user in the urban environment, they might receive a signal from a satellite that is in line of sight. In this scenario, as we query along the ray between the user position and the satellite, then we get from the neural network a prediction of low blockage density. However, when we have a satellite that would be blocked by the city, we will get peaks in the blockage density at the sides of the building, in addition to relatively high density in the middle. So this would correspond to strong blockage or a non-line of sight case. And in that intermediate case where we quickly pass to the sides of the building, we get moderate blockage where we get peaks in the blockage density, but they are not quite so spaced. How we make non-line of sight predictions is to then convert this to a depth value. So in the satellite 1 case, we have low blockage density throughout the ray, meaning that we have a high depth that we can see along this ray, and this corresponds to line of sight. However, when we have blockage in the way, we predict a lower depth, meaning that there's object close to the user. And this is the primary feature that we will be using for non-line of sight prediction. However, we have to be aware of that second challenge, that unobservability haze, which need not be far from the user. In such a case, we get higher blockage density close to the user, which impacts our depth estimation, meaning that we think that there's an object close to us when in reality it's just the haze. In such a case, we might need features that are depth agnostic, meaning that we need a feature that characterizes the haze differently from the building, even when the haze is close by. In such a case, we might notice that the neural radiance field tends to highly prioritize concentration and depth at the surface of objects, meaning that the obstructing objects tend to have higher peaks in the blockage density than the haze would. And as a result, we propose these two features, a maximum density feature and a sum density feature, which allow us to, in a sense, peer through the haze in a way that's depth agnostic. So with this in mind, we will now be moving into the results. We'll be discussing how we train this neural city map, and then discuss how we do this GNSS non-line of sight prediction. Specifically, we chose the setting of a Google smartphone decimeter challenge, and specifically a part of the Google smartphone decimeter challenge, which is in a more urban area that also includes vegetation. This specific part is in San Jose, California. We start with Google Earth Studio images of the scene, specifically 800 of these images at fairly low resolution, for a total memory footprint of 230 megabytes. These images are all taken above the building, mimicking what a drone might see if they were to fly in a circle above the building. We then train a neural city map using NeRF Studio with the NeRF Facto model architecture. The total training time is 1 hour and 9 minutes, though anecdotally we observe that is most of the way through training within roughly 10% of training. The neural radiance field that represents the neural city map has a total memory footprint of 168 megabytes in the standard PyTorch format, though we note that even if you add more images, that memory footprint will stay constant, a key advantage of this representation. We train it on an NVIDIA Tesla GPU, and during training, the whole NeRF Studio application takes 4.43 gigabytes on the GPU. One of the key things to be aware of, because we're training with Google Earth Studio, is that vegetation has different artifacts than we would see in the real world. Specifically, in Google Earth Studio, we get regions that have floating vegetation, as well as the vegetation looks a lot more opaque than it would in real life. So comparing the Google Earth Studio image on the left to the Google Street View image on the right. Now, at runtime, we only have to query along the rays to the satellite, as shown in the methods section. However, it becomes difficult to see what the neural network is predicting if we only, say, show 30 rays for 30 satellites. Instead, we turn to the Fibonacci sphere algorithm to provide a more uniform distribution over the sphere to visualize what is happening with this neural city map. Specifically, we use 3,000 points per hemisphere. And the nice part about this Fibonacci sphere algorithm is that it mimics a sunflower, allowing us to pack it along the surface of the sphere in a way that's much more uniform than you would if you, say, would query uniformly along latitude and longitude. So with this in mind, if we plot the upper hemisphere of what we would predict at ground level near where the Google smartphone decimeter challenge is, we see that we visually see the scene in RGB on the left and in depth on the right, but we also have this unobservability haze in the middle. So the depth is a really good feature for the vegetation and the buildings that's nearby. However, this unobservability haze causes some noise that would impact our non-line of sight prediction. So instead, when we look at the other features, the max density feature and the sum density feature, we can see that the max density and sum density features are able to sort of peer through the haze in a way that the depth feature cannot. And this allows us to improve our non-line of sight predictions. Specifically, if we look at these features pairwise, we see that there tends to be two clusters. One cluster with obstructing objects, such as the building and vegetation, and then the other cluster being the unobservability haze. So specifically, the obstructing objects tend to be closer to the user and have higher peaks in the blockage density. And as a result, we see a cluster here for the obstructing objects, cluster here for the obstructing objects at low depth and high blockage density. But when we look at both of the depth agnostic features, we see a more interesting view where we see the unobservability haze tends to be low in both of these. And during the training process, the neural radiance field will choose to prioritize to put high blockage depth at the surface of the obstructing objects, which causes both features to correspondingly rise, allowing for this more spread out and clear cluster in the obstructing objects. So to perform the non-line of sight prediction, we take these features and apply a threshold. And if we apply this threshold in depth, we see that we have consistent depth predictions for the nearby vegetation and building. However, the haze can cause some mispredictions and hence a mismatch depending on the threshold that we choose. Then when we look at the more depth agnostic features, which are the max and sum density features, we see that the haze above us does not pose as much of a problem. And we see more consistency between these two features in the mismatch comparison on the right. So in summary, we introduced this idea of a neural city map to the urban GNSS localization community. Now, this neural city map is trained from camera images, but we show that we can extend this geometric understanding of the scene produced from camera images to improve non-line of sight predictions in a GNSS context, allowing us to more efficiently navigate in an urban setting and use this urban environmental features to our advantage. We then compare three key features that we use for GNSS non-line of sight prediction, specifically the depth feature, and then two depth agnostic features, the max density and sum density features. We then demonstrate this GNSS non-line of sight prediction with the Google Smartphone Decimeter Challenge dataset. With that, I want to just quickly highlight some of our related works at ION GNSS Plus 2023 that we encourage you to visit, seeing that you're visiting this presentation. Specifically, on Wednesday, we have a presentation from our co-authors and our lab related to navigating on extraterrestrial environments and using a neural radiance representation. We also have a very closely related work on Thursday related to how we construct neural city maps from multiple regional neural networks and how that compares in the visual domain rather than, in this case, was the GNSS domain. And lastly, on Friday, we encourage you to go to our lab session related to the open source Python GNSS library, which we use for a lot of the data processing in this presentation. I'd also like to acknowledge funding from the National Science Foundation, which made this research possible, as well as the incredible community of the Nav Lab here at Stanford. We also like to have some special thanks to Aryasha, to Adam, Ashwin, and Derek, who helped throughout this project, providing insights and truly enabling this project to happen. And with that, thank you so much, and I hope you enjoyed this presentation on how we can use neural city maps to improve GNSS non-line of sight predictions in urban environments. Thank you very much.